So welcome back to the afternoon. If you have a PhD, you should leave the room and come back in 30 minutes. And now we have a free talk from Jun Lee from
Yesterday somebody was asking what perfect obstruction theory. Okay. What does it mean?
And let me ask any more. Which example is good? And I try to avoid it, but okay. So that's the topic I try to avoid in the whole talk. Okay, so let's just try this and start with so what is virtual cycle? You have to go through. Okay, let me tell a story. I mean, back now we're talking. Trying to put a virtual cycle, the Prometheus theory, and I invite Bill Bolton to give a talk at Stanford. And I still remember, he was sitting in my office, and I said, I try to do this. And then he said that go study the normal quantum structure. So I went there and opened his book and just looked at about 10 pages. Okay, it's a whole book, right? And I only look at a particular section about the normal quotes and just look at these 10 pages and I work out a select example and then that's the idea. So what is the normal quote? Let me do the example. So this is the first example where Kunsevich did for the G0 case. Is it better? So that one. Oh, that one is for the recording.
Yeah.
Sorry, I cannot do it. So let me just try my best, okay? So what we want to do is we want to do the 0 goes to the quick between D, and we know that in the virtual cycle, and we know the degree of this one is going to be the 0 degree D the movement and balance, right? Then you write the quick to be inside C4 defined by W5 0, which is x15 plus x5.
What's the dimension of this M0? Is this a zero dimensional thing?
Yeah.
Or virtual dimension 0?
This we don't ask the dimension of the modular space because the modular space we deal with usually is very complicated. Okay, it has many components, it's different dimensions. But what we ask, what is the virtual dimension or the expected dimension of M bar 0 Q5 and this is the okay. So I'll explain to this one. So how Kunsevich did this. Okay, so let me just. There is a way to understand the quintet. Quintet is a hypersurface inside P4. So let me just draw a picture like this. So I have instead of looking at the stable map going into the quintet, I look at the stable map goes to T4 of degree B, and those that maps to Q5D will be a sub, right? Okay, substack. Now inside this one, it's a stack, but whenever we have a modularized space, the universal family is going to be, because every point inside this one is going to be something like f from a curve goes to P4, right? So I can line up all of this curve to be a family of curve over this polymorphic stack, and then I can line up all this map F to be, say, capital F, pi, and this is going to be the evaluation map that goes to P4. Okay? So this is the universal family, and then over P4 we have O5. O5 has a section which is W5, and the vanishing is going to cut out with the Q5, right? So inside, you just write the Q5 is W5. Okay, all of this data, we can do this. Okay, so we can pull back the shift, so we get F pull back O5. That's a invertible shift over C, and then I can do a direct image push forward. So that become a shift, but I think of it as a vector bond. But actually, it is a vector bond because the push forward is a locally free shift because I'm doing it in a zero case. So I can do this one here. So now, here the point is that this is a dimension 5D plus 1. And if you check this one as rank 5D plus 1, and then I have actually, oh no, sorry. This one actually is the arrow is going to this direction, right? I'm pushing it here. But then after I have a section, I can pull back this W, and I actually get a section I will call FW5. So I have a vector bundle sitting over this one, and I have a section of this bundle, and this one is exactly equal to the vanishing of this section. Okay, so this is the data outcome. I want to cover. Actually, I should be slightly more. So this one actually is, okay, what I want to work at. This is the modular space we want to understand. We can embed this one in a smooth space, and we note that also this one, after embedding, the image actually is the vanishing locus of a section of a holomorphic vector bond. Okay. So now this is the typical sort of intersection theory phenomenon, right? So what is the exact intersection? So let me say, if you open the Holden's book, so you have a, say, proper, project a scheme, you have a vector bundle, so this is the N, this is the R, and you have a section S here, so you take that X equal to S inverse 0. And in general, so this is a pure smooth, and this is a vector R vector bundle, and you know this, you will say the expected dimension of X should be equal to N minus R. But of course, you know the dimension of X can be anything, right? S could be just a zero section. But then the question is, we want to know what is the cycle. And if we just do a cycle, it can be, there's no answer. I cannot give an answer without giving the information of S. But what is the virtual cycle? Virtual cycle meaning that we want to take the fundamental class of X when the section in the general position. Okay, so if you go, when we say it's in general position, even though algebraically maybe we can never find the S, maybe it's a negative bound, so that has to only have only zero section. But still, we can talk about the Euler class. We talk about localized Euler class, chunk class. That's all technique developed to say what is this one. This is just going to be the Euler class of E, right? Or you can say the top chunk class is going to CR then E, Euler and then it's equal to, we can to localize, so these are going to be the class inside some W, or we can even localize. So it's going to be CR with section, but that's going to be A minus R X. And this is going to be our virtual cycle. And that's the conservative formula. So I'm just-
So CRV is the top term class. What is CRE, comma F?
CRE is the top tree class which lives in the W, but CRE is only live inside the vanishing locus of F. We sort of localize, and there's a local tree class construction. Oh, F. No, that's S. Sorry, that's S. Yes, that's no, it's not my fault. So that's the defining equation. So in this sense, so if you look at this one's embedded inside 5D plus 1 dimension smooth object, and it's cut out by a 0 section of the rank 5D. So the expect dimension of this one is difference here. So that sort of course, this is not a precise proof, but it sort of gives you an indication that expected dimension of M bar G 0 and 0 here, Q5 D is equal to 0. With the difference of the dimension and the virtual cycle. Okay, so it's just as simple as this, except that here we have an embedding of a modularized space. We have a defining equation of the modularized space, and the defining equation is the global defining equation, and everything should be lined up. Okay, and in real situation, we have such a nice package. Usually, you probably know how to construct modular space in algebraic geometry. Well, in analysis, you're going to all smooth maps. You have this. But in algebraic geometry, say you use GIT, or right now you just abstract say this is a group point that's a stack, and you don't have embedding. Even though you prove this one is a projective, say you have a projective embedding, but then why this? How you can get this package? But if you get this package, but then you ask the question why this is the right thing. I mean, other people may come up with another package and they got totally different. So what is the point of the whole thing is that okay, so now virtual cycle without parent defining embedding and equation. So this comes to the next thing. So I have to come back to this picture again. So this picture is E goes to W, and you have a section S, and X equal to S inverse 0. And you wanted to say what is the term class, let's say C, so this is R, CR, E. So you have to you do the information to normal form. So this is McPherson and first construction and this is for this block. So what you do is this, right? So let me draw the picture here. W here, and that's a E here, and you have a section here. That's S as a graph of the section, and this is where the X is, right? So what you do is you say what is the normal cone to X inside W, which is supposed to be a cone subscheme of the E restrict to X. Okay. So eventually, you should think of X is going to be our moduli space. This is the space we want to construct a virtual cycle. And you keep in your mind, we don't have the W eventually, right? I mean, the case here, so in this case, this is going to be like a W here. Use a different color chart here. So this is my W here, and this is my X here. And I want to construct a virtual cycle here. Here I'm having a W, I'm having an E here, I'm having a section S. These are the first situation. Okay? In general, we're not going to have W, but what to do is that the normal cone construction say that we can do this. First, we construct this one here, and this one. The one easy way to say this in this particular case is just going to be the limit t goes to 0. The t inverse s. So what you do is you just scale the section with t inverse s. St is very small, and you eventually get a limit. You deform the graph to a normal cone. Okay, this is called deformation to normal cone. You get this one here, and because only the limit, the cone will only be support over where the section is 0, right? Outside is going to be. So this is the cone, and second, then the Chern class of E, R, S is just going to be now. This is a cone inside a vector bundle over a very similar scheme, but nevertheless, it's a cone inside a bundle. We can intersect this cone with the 0 section, because the 0 section has normal boundary inside the total space. So we can do the Jissing map. 0 section E restrict X of this cycle X W. And this is the inside A minus R X. Okay, so that's the localized true class. So in the end, we're going to have this. And to get this one, we need this. Okay. So now, so the slogan the key point is that you have X, which is any modular space, That's a perfect. So let me just write the cone. So this I write N, but let me just use cone. That's standard cone. Cone of X inside H1 by H0 E. Okay, I'll explain the notation, but let me first write down the statement. 20. So this is the intrinsic normal cone into the Barlow stack. So this is the Barlow stack. Okay, table 9. Okay, so the perfect obstruction theory, I never get the arrow right, so let me say. So this is the continuum complex of X. So I have to go the other way around, so I have to remove the complex. I'll explain the initial sentence. So first, what so far I did is that what I said is that if X has a perfect obstruction theory, a perfect obstruction theory is a data like this. So this is a potential complex. There's another complex which is have to be perfect. It means that it's locally can be equivalent to a quasi-equivalent to a complex of locally free sheaves. And then once you have a perfect obstruction theory, then you will get a canonical intrinsic cone inside this one. This is a stack, but actually it's like a vector bond, just like a vector bond. And then so the virtual cycle is going to be the zero set, is the Gissing map, right? There we have the Gissing map. We have the Gissing map. So this is a stack, but it's a Barlow stack, so you can treat it just like a vector bundle. The theory about vector bundles is Gissing map of zero section still works. So you take the zero section of this Barlow stack, and you take the Gissing map of this cone. This is the cone, so it has a cycle. So this is CX. Okay. So I erased the things, but you can just compare. So this is a why I do it for compare. Not happy with Barlow stack, that's fine. If you want to need it and you can spend 1 week, you'll be happy. But for the moment, if you've never seen that, just say it's a vector bundle. Okay. And you have a code inside vector bundle, and you can do the section theory. So the thing I wanted to say is that for the Gina zero case, once we have the embedding Q5E is going to be if you have an embedding like this, and it is consistent with the perfect obstruction theory, this cone, the cone I talk about, the intrinsic cone, is just going to be this cone. Okay? And I mean, the Barlow stack is just going to be this one. I'm just taking the ordinary thing here. So more complicated situation, I don't have W here. And I don't have this graph here. But I don't even have a vector bundle over here. But still, if I have a perfect obstruction theory, so hold on to perfect obstruction theory until the last minute. Okay? If I have a perfect obstruction, I still have a bundle here, which is going to be, and then I need to construct some cone sitting inside this. And that cone and this one has to be constructed, but somehow the theorem says that if I have a perfect obstruction, I do have such a cone, intrinsic cone here, which is canonical. And because it's canonical, then once I have this pair, I just do an intersection. Now the question is, what is this? What is the perfect obstruction? let me talk about the perfect observation first, and then answer your question. Okay, because your question is you know, as a consequence, why you have to have a perfect obstruction. We will always have a normal cone in some sense. Okay. I'll hold on your question. Okay, but let me continue. Okay, let me just say this. I don't want to go to the steps. Just example. This is the example I'm going to talk about. So, for instance, if I fix a curve C, a line bundle here, and I want to study deformation of section. So, okay, so let me put the say X to be the space of normal section. So the tangent space, so the first order deformation is H0 L. I mean, this is sort of misleading because it's a smooth space, but still, if you have done a little bit of algebraic geometry, you know, if you vary this L, if you vary the C, there's going to be some section may not persist, right? When you vary the line model in the base. And then there's obstruction space to deforming L as section, and the obstruction lies inside H1 and H. Okay. And the automorphism of S inside H0 is 0. And the point is that no higher obstruction.
Where are you defining? We're defining the line bundle on a fixed curve?
You can, I mean, I'm doing relative, so you can let the C vary, you can let the L vary, but I do the relative obstruction theory. So in other words, I look at when I fix this one, what is the tangent space, what is the obstruction, and so the thing is, you know, you just use Chuck for volume. First order deformation H0, the obstruction will be H1, and you know H0 L1, and then the next obstruction series should be H2, but H2 is automatically 0. Okay. So to answer your question, the obstruction space HL.
I have a curve that I want to deform a line with a line. Then it's always just the deformations are always just parameterized by H1 of the canonical function, right? I mean, regardless of what's line bundle is. So why are you saying H1 of L?
No, the space of deforming the sections.
Well, you're deforming the sections.
Now, this is misleading, but that's the simplest case. That's the one I'm going to use. The sections, okay? Now, if this is not, this is a surface, then I do have the next cohomology. So this is not going to give you a perfect obstruction theory. Why perfect is important? Because by base change theorem, you can take the R1 pi rho star of this one. This is going to form a sheaf which satisfies the base change property. Because there's no high cohomology, right? There's a base change property in the Harshman property. It's overlooked as and because of this, because the obstruction sheaf has to satisfy the base change property, then all these local cone will line up in a reasonably nice way so that you can talk about global intersection. So in other words, when you do obstruction theory, you can always make sure that the object has no infinite automorphism. Okay, there's no automorphism, so it's in the Riemann stack situation. And then you calculate the first order deformation. The linear first order deformation, you always come up with a homologous, right? And then usually, then you see when you have certain deformation in your algebra theory, what is the obstruction? And what always comes to the next homology. You know, when you do the sheaf, it's ext. When you do the, when you deform the x, it will be h0 of tx, h1 of tx. So this might change. But the point is that once you have this homology, you don't want any further homology. In other words, the dimension of the difference of this one has to be a Riemann-Roch number. Okay. So if this is sort of a verbally, if that's the case, then we're in the perfect situation, in the perfect obstruction theory. So in other words, if we do have this one, this has to be perfect. So it has locally only two terms. There's no zero term, and this automorphism, and that's first order. We do have obstruction, but with no obstruction, we get a smooth modular space. We know how to do it, but that's just one step further, a little bit with obstruction, but not high obstruction. Okay. So the punchline is that once we have the perfect obstruction theory, we can construct a cone inside a vector bundle, like in the genus zero case, without knowing the embedding data. So if we have embedding data, then we can construct it. But then another catch is that if you put a scheme, you put an embedding data into a big scheme, defined equation, that will induce you obstruction theory, perfect, or sometimes perfect obstruction theory. Different embeddings will give you different perfect obstruction theory. They might be equivalent in this sense, or they might be not. Okay. If they are equivalent, then they give the same cone, they give you the same cycle. So the obstruction, the virtual cycle does depend on choice of perfect obstruction theory. And that also explains why I can just go ahead and go embedding to define equation, because when then you pick up something else, you get a different cycle. So the modular space, the good thing is that almost always it comes up with a God-given obstruction theory. And you just have to work with it, and then there's a virtual cycle. Sometimes you may a little bit modify it, okay? But nevertheless, the obstruction theory is canonical, and if the obstruction theory is perfect, then the cone and the bundle stack is canonical, and then the cycle will be canonical. But the way it's constructed is so awkward, and how to construct it, that's a huge challenge. That's simply not solved.
Can I ask you a moment? So you define this vector bundle stack to be H1 not H0.
Yes.
Can you explain a bit more about, if I have this complex, how do I think about H1 not H0?
So this basically is, I did mention I have two complex, right? So basically like this one here, I'm going to so for instance, so if I have a modular space of this CL or whatever, then I'm going to have a complex E, the 0 goes to E1, such that for any point S here, so that H0 of right, this is E, so this is S2 perfect obstruction theory, you restrict to C infinitely H0 of L H1. So in particular in this example, we can easily write down two vector bundle arrow between them, so that the kernel, the kernel, restrict every point just give you this. And then it is just H1. Now here is the one, this is a Carl-Baron and Fantacci. You think of this, it's a vector bundle. You think of this is a scheme. Okay, so it's a dynamical stack. You think of this as a group point group, and this is action on it. So you really H0, E, and then E1 function by E0. Okay, this is the RD stack. And this you can do locally, but if you take a different precise isomorphic representation by locally free, the quotient will be still the same. So this is the point is that if you do because this one is not canonical. Again, the point is you want to find some canonical object. This is not canonical. This